Okay, let's go ahead and start. How'd you do on this, do you feel like? Okay. So again, we're obviously nearing the end of geometry. There will be some factoring in this unit, but a lot in Algebra 2 as we start in January. So good thing to keep reviewing. When it says solve, it means find the zeros. That's really what we're saying when we say solve a quadratic. How do we know it's quadratic? Yeah, Zeke? Yeah. Zeros are the x-intercepts, or where the function has a y value of 0. And yeah, so we know it's quadratic because the highest power of r is squared. And it's kind of, you have to say it two ways. It's there, like the squared is there, but also it's the highest power. So we want to set this equal to 0 first. So we'll add 30 and subtract 11r from both sides. So we'll get 5r squared and then minus 55r plus 150 equals 0. Okay, then I would recommend using the star or something like it. If you have your own method, that's fine. So in the star, remember we multiply a times c at the top, b at the bottom, and a on the sides. What is a times c in this one? Oh, but wait, what do we have to do first? Good job, way to go. So GCF factor this, which makes this a lot easier. So what is the GCF? It's 5, yeah. Okay, so if we pull a 5 out, we're left with r squared minus 11r and plus 30. Now we just star the inside, and that makes this a lot easier. So what is a times c? 30. What is b? Negative 11. A is 1 inside. So we're looking for factors or numbers that multiply to 30 and add to negative 11. And which ones are those? What multiplies to make 30 but adds to negative 11? Yeah. So sign can be flexible. We're just looking for those positive and negative numbers. By the sign being flexible, what I mean is find what makes 30, like 6 and 5, and then adjust sign as needed to match B. Okay, then we want to reduce. So reduce the sides if possible, but these are already reduced. And so we get x minus 6 times x minus 5, still equal to 0. Now what? Well, it's something times something equals 0, right? So something has to be 0 for that to be true. So we just find out where each of these are 0. And we find 6, and we find 5. And since there's no geometry involved, that's 2 acceptable answers for this one. Raise your hand if you got both. Okay, awesome. Well, a quick check-in on Friday's work. What'd you think of using the clinometer? Which is a little bit, I figured out how to do it on mine where I could hold my finger on the lock button and then when I released it would lock it. That way I could look. And I don't know if everybody had that option. Otherwise, it's kind of hard to use by yourself. Okay, but it was working pretty well for me. So, what do you think? Raise your hand if you liked the shadow method best. We had 3 methods now to do this. Okay, raise your hand if you like the mirror method best. Trig method. You're all going to vote one of them. So I have 2 votes for trig. What about the rest of you? We're going to do it again. Shadow method. If I said go measure how tall or high something is, that's 2 of you. Okay, mirrors and trig. Okay, that was most of you. Did you find it kind of the easiest to set up, or at least to do the measuring? Which is why I like it. The calculations are longer, but the measuring is typically easier. I know you guys struggled with the app some. Yeah. And again, by the way, to make, I don't know if I have a protractor, but I do. To make one, you stick some kind of a tube, like a pen, the barrel of a pen, or a straw, like just tape it on to a protractor, the straight edge. And then from the hole, you tie a little string with a weight, like maybe a nut or a washer or something, or anything else. You could even just hang a pen down here. So as you turn this to look, and you use the barrel of the pen as you look through that as kind of a scope, well, the string stays plumb, stays straight down, and it tells you your angle. So it's easy to make if you have string and a straw. Okay. So Lyra, whenever you need to find how tall something is, just make your own. I have a protractor you can borrow. And our heights were all pretty much around 30. I think you guys remember 28. I think you got 28 and a half. Oh yeah, you were gone. That's why it was such a good day. You guys got 29, yeah. And then you two got 28 and a half-ish, I think. Oh, yeah, you weren't here. And then, do you remember yours? Anyway, point is, those light poles are roughly 30 feet. And that's roughly what you guys got. So it's a good method. The angle has to be measured accurately, though, and that if it's not, it can throw it off pretty badly. So now you kind of have a feel for how we use indirect measurement in the 3 different methods. And what do you think? It's kind of a cool process, do you think? Yeah? Okay. So our new unit is all about circles. Okay? Circles are surprisingly complex. Not the actual shape of them, but all the things that we can learn about them. Here are some sample words that you'll be learning. Radius, diameter should be familiar to you, but secant, chord, and tangent, not the same tangent as what we've been using, but those are new, and that's just a sample of what will be new. I do need to tell you going in, this is a fairly beefy unit, and there is a lot of new stuff in here. A lot of relationships, vocabulary, and concepts. So please study your notes, because hopefully we know by now, that just having the notes is not really helpful unless you know what's in them. So you got to go home and read them so that you know where stuff is. Make sense? Okay. This unit will probably not conclude until after Thanksgiving break. I would guess. I don't think we're going to finish it before that. We'll try, but we'll have to be fast if we do that. And then also, maybe I'll just draw this. There are triangles in circles as well. For example, if I draw in a radius here that's perpendicular to that secant, well, now we're creating a triangle right there and right there. So all of our triangle relationships, well, most of them, will still need to be used even though we're talking about circles. In other words, please don't forget your right triangle trig. Please don't forget potentially your similarity relationships, that kind of stuff, okay? But especially Pythagorean theorem and right triangle trig. Don't forget that. That's going to be used in this unit as well. But it's cool. Like, I knew stuff about circles, but until I started with teaching geometry, it didn't really sink in about how cool they are and all of the things that we can use with them. We'll start with the basics, at least some of it should be, and hopefully a review, which is to say things like diameter, circumference, radius, area, those kind of things. And then the equation of a circle, I imagine, is new. Has anybody ever seen that before? Okay. So that will be part of this first section. So I want you to note, it says topic 10, and then it says 9.3. So 10 is all about circles. 9.3 is a brief little section on coordinates. Coordinate geometry, we called it. We did some of 9 when we did coordinate proofs of polygons. You remember that? Of the quadrilaterals? And I said, here, find 6 slopes to prove that this is a rhombus or something. Do you remember doing that? Okay. That's coordinate geometry. So coordinates, we're going to see some coordinate pairs on graphs and be able to write equations for circles. It's going to look a little bit algebra here at the beginning. After that, it doesn't. What do you remember about circumference and area in circles? Anything? Okay. We're off to a good start. Let's go put some stuff down. So you have it. And we're just going to call this whole thing Unit 10. And just circles. Probably it ties for my favorite unit in geometry, or maybe second favorite. It's cool stuff. Okay, we'll start off with some review, hopefully. Diameter, distance across through the center. The through the center part is what separates this from any other chord. So this is why, if you took the notes from me, this is why all these circles are here. We're going to draw a bunch of these on there. Okay, what's a radius? Yeah. So this is the distance from center to edge of a circle. And it is 1/2 the diameter, or the diameter is 2 radiuses. You probably see it that way more often. I'm going to go up here and put a D on this diameter just to separate D and R. Sounds like you probably have done those before, I would hope. Is that true? I think, like those, after you're done with this geometry class, those need to stick. Okay, like radius, diameter, and actually the next 2 things, circumference and area. Those do come up, believe it or not. Okay, circumference, what does it mean? Yep. So the distance around the outside of a circle. It's the perimeter of a circle. It just has a different name, and that's because it's a circle. So the equation for this is going to be pi times diameter. Now, where did pi come from? You guys are familiar with pi? Yes? What's the approximate value of pi? Yeah. Now, we know, well, hopefully we know that pi is an irrational number, so it goes on forever and ever, never repeating. So when we say 3.14, it's an approximation. That's why I'm doing the squiggly equals. It's an approximate value for pi. Okay, again, this is the distance around the circle on the outside edge. Since we wrote up here that diameter is 2 radiuses, we could also modify this formula to be 2 radiuses times pi. So 2 pi r, you might see it that way. The space inside, or the surface inside of a circle. So this is, anybody know? Pi times radius squared. Okay, I'm going to write this out to the side. You need to memorize these. That's just functional human math right there, okay? Don't be Google dependent. Do those look familiar? Yeah. All right, so back to this then. What are the circumference and area? Well, as usual, you need to write your equation down first, then solve. Like plug in and then solve. Because what if I tell you a circumference and ask for the radius, or tell you a circumference or tell you an area and ask for the diameter, those kind of things. If you're not writing both sides of your equation, you won't have a place to plug in. Now, one other thing, I'll show you what I mean in a second, but one other thing to talk about is this. Let's do the circumference of this blue circle. So C equals pi d. That's the circumference, right? The formula, I mean. But we're not given the diameter. So what is it? D equals 10 centimeters, right? It's not told, but we know it's twice the radius. So plug in 10 for the diameter and pause right there. So this is 10 pi centimeters. Don't forget to label. This is the exact circumference. We've seen this before when we have square roots in our math. The exact value versus the approximate value. So if you're maybe working behind the scenes, designing as an architect or an engineer, you might want to leave your answers as exact and then let the construction workers approximate it. Okay? Or maybe like the people who do not inventory, but pricing of the job or that kind of stuff. Because mathematically, 10 pi is perfectly accurate. It's right on, in other words. But if we want to go maybe cut something, like let's say we're putting some of this, if you look on this table, there's this veneer on the edge of the table to make it look nice. If this was a round table, we would need to know that how long the circumference is so that we can know how big to cut that. You can't cut 10 pi, can you? So how do we make it approximate? or maybe a few other digits of pi. And now we say 31.4 centimeters. And that is the approximate circumference. Okay? So think office math versus Home Depot math, right? Or office math versus job site math. Maybe engineer says 10 pi. Construction guy says 31.4. Not that they're super different, but big thing to think about here is not for the engineer. If your calculation ends at 10 pi, it's probably fine to make 31.4. But if you need to take this calculation to the next calculation and the next and the next and the next, if you've approximated, that approximation is going to be compounded by the time you get through all the calculations and maybe be significantly different. 10 pi stays perfectly accurate. Also, mathematically, sometimes that pi will cancel off and you don't even have to deal with it later on, which is nice, okay? There's a lot of good things about leaving pi in your answer. That's how we say it. Leave pi in your answer. Okay? But again, if you're out there about ready to cut the piece of wood or cut the sheet metal to wrap around, 31.4 centimeters is what you're going to cut. Any questions on that? It's an important distinction, and you need to read the directions for these problems carefully so you know which one that I want. Okay, we can do the same thing with area. So pi r squared for area. A equals, make sure you're writing both sides down. Pi, the radius was given in this case. So 25 pi. What do we label area? What? No, that's length. Centimeters squared. Okay? So squared units for area measured in squares. This is the exact area. Again, maybe you take this calculation to the next thing and the 25 pi is what you need. Or maybe pi cancels when you solve for the next thing. Okay, or we can do 25 times 3.14. Does anybody, yeah, you have your calculator. What is that? 75 or so. 76 maybe. 76 point something. 78 point something. 78.5. Okay, now we say 78.5 square centimeters, which isn't very big, but maybe the construction person is painting or sheathing something and it's this little tiny thing. That is the approximate area. Okay, so conceptually maybe it's new, but notice that the exact version is less work. We don't actually need to do the extra step of multiplying by something. We just stop there. It's less work. So like the exact version, it's better. It's mathematically better. Maybe not practically better, but it is mathematically better. Questions on that? Okay, go ahead and run through that same idea with this circle. So circumference and area of that one on the right. There's your check. 18 pi for exact circumference, 18 pi inches, and then 56.52 inches for approximate. And then for the area, 81 pi square inches for exact, and 254.34 square inches for approximate. Good? When do you use exact? When you're not cutting, is that what you said? No. There you go. Office versus, should we label that? Office job site. Good? All right. So let me give you a quick example. Maybe we know the area of something, so the area of a circular, you can write this down if you want. This won't be too long. Table is, you know what? I might even change it a little. A little bit more. So the circular table in your dining room needs what's something realistic here? Do you think refinish has a hyphen?
Yeah.
Kind of looks like it needs one, huh? Anyway. What is the diameter? Okay. So 1 minute on that. Okay, first of all, like in terms of thinking, what is this a measurement of? Yep, this is area. Okay, so we want to start with our area formula. Both sides. If you only write just, a lot of students, I'm telling you this, and I tell all my students this, a lot of times students just focus on the process side of the equation. And they just write pi r squared. And then here's the mistake they make. They take the 2000 and they plug it in for r, and they think that's their answer. But if you write both sides of every equation, every formula that you ever deal with, write both sides of it. And that's not just for math, but for physics, for chemistry, economics, whatever. All your engineering classes, those of you who are going to do that. Medicine classes, if you take those. Write both sides of formulas so that you can plug in both ways. Because we know that it goes here. So 2000. Okay, how do we solve for r then? This is now an algebra problem. Fairly routine algebra problem. What do we do? Good. Leave it as 2000 over pi for now. Okay. And what do we do to get r by itself from here? Square root both sides. And you could, like if I said office version, it would be this. It's just the square root of 2000 over pi. We could simplify the radical, but its office version is that. But otherwise, we take that now to our calculator. Huh? I know, we're not done yet. 2000. By the way, most calculators have a pi button. This one has it right here, which will use more than just the 3.14. It goes out several digits. In fact, let's check what this one does. So it goes out, what is that, 3, 6, looks like 9 digits. So it's a little bit more accurate. I mean, it's not tremendously different. But anyway, 25.23. The question actually asked for the diameter. Yeah, we're going to finish. Not for this. 25.23, what's the diameter though? That's what the question actually asked for. Yeah. So 50.46, what's the unit? Inches. Okay. So that's just an example of why we write both sides of the formula down. Okay, so basically what we've done so far is review, because circumference area is not a geometry standard, but it's important stuff in life, and you need to know how to find those. And then the new stuff here is the exact versus approximate. Anybody know what the numbers on your tires mean? Let's bring this back to reality again. Here, let me show you a picture. Now, they're not usually printed that huge, but that's what they usually look like. Yeah. He said that how thick the rubber is that what you said? So to me, that would mean if I cut in here, how thick is the actual material that it's made of? Good thought. That's actually not what it tells you. Good try though. Okay, here's the names of it. But we have to know what those mean. So P is passenger. So if you go out and look at like whatever car you get picked up in, unless you ride the bus, it should say P. Okay, section width is measured in millimeters. And I know like that's one thing that's hard about America is sometimes we mix units. Like a lot of engineering is done in the metric system, even though we live in America. Anyway, that's the width. Let's see if I have a picture here. That would be like on this tire, that would be the width this way. Like across the tire, okay? So that's, I'll just try to draw it. Let's say we're looking end on a tire. It's this way, section width, okay? Aspect ratio is this. Height, they call it. What fraction of the width is the height? Does that make sense? So on this tire, this one is 225 millimeters width-wise, and the aspect ratio means that the height is 75% of that. Okay, so it's not quite as high or tall as it is wide. And that's from the rim to the edge of the circle. Okay, and then the R stands for radial. It tells you what kind of tire it is. It has a radial inside there. And then the 16 is your rim diameter. So this, I need to get a good color here. This diameter here is 16, and now that's measured in inches. So you see the unit combination of millimeters and inches. It's weird. Okay. So one thing I'd like you to do tonight is take a picture of whatever car you ride or have as a family, or if you drive. Does anybody drive yet? Okay. If you drive, take a picture of this information on your tire, please. Okay? Okay. And then we'll come back and do the problem, how many times does it roll as you drive. It's good information when you go buy tires, this is what you have to tell them, or they will help you, but you need to understand what you're buying when you buy it. And like bigger vehicles, the radius of your rim would be bigger. 16, like my truck is 20. What do you drive? So it's probably 18 maybe. Okay. Also, wider tires. You know, some guys like to put big wide tires on their trucks. This number would be different. Some people like to put those real thin rims. You know what I'm talking about?
Yeah.
Like they're kind of where the tire part is real skinny, real thin, I would call it. You know what I mean? I could look at a picture, but that would mean this aspect ratio is way smaller than 75%. Anyway, it'll be interesting to compare. So I guess along with taking a picture of your tire information, also please bring the name of the tire, of the car, so we know what we're dealing with. Like, is it a Honda Accord or a giant pickup? Okay. Any questions on that part of your assignment? Just snap a little picture, and then we'll come back to that. So, grab you should have your notes. This is going to be brand new. All that stuff was reviewed. This is brand new. So, equations of circles in the coordinate plane. Like I told you, we start off this unit. You can see an XY coordinate plane here. And then after that, all of our circles are just circles. Just pictures of circles, like back in geometry mode. So, what mathematical equation could you plug into Desmos for it to graph a circle? That's what we're looking at here. Everybody clear? And there's some letters on the points involved. And these letters will come up again in Algebra 2, the H and K. And obviously XY is always there. So let's, I think, just go to your notes and put this in there. So for this one, go ahead and put that, if you're doing my notes with this format, go ahead and put that circle at some point on an XY grid. The one in the example picture and this one, they're both in the first quadrant. They don't have to be, they can be in any quadrant, or they can span across several quadrants. And then we need to label HK and some point on the circle, just call it X, Y. So for a circle, it looks kind of weird. X minus H squared plus Y minus K squared equals R squared. You might say that you see some similarity to the Pythagorean theorem there, except these variables are now specific to a circle. So we need to define what H and K are. Can anybody tell me, just based on what we've said? Or what we've drawn, I should say. Yeah, good job. Okay, so we'll say where H. Okay, let me fix that H. Okay, and then XY is some point on the circle, on the edge. So you'll need to be able to do two things with this. Actually, more than that. 3. If I give you the equation, you need to be able to tell me where the center and the radius are. 2, or like number 2, you'll need to be able to graph circles based on an equation. And number 3, you'll need to be able to write the equation if I give you either the center or 2 points, or if I show you the graph. You need to be able to write the equation. That's the hardest of the 3 things. It's not that bad. I'm just saying out of those 3, it's the hardest. So let's go look at a couple examples then. Note that that one has parts of the circle in all 4 quadrants, centered in the first quadrant. Okay. Start off with an easy one. I don't think we need to put examples like this in our notes, but I will put one of writing an equation in there. So what are the radius and center of the circle with this equation? Well, I would do it this way. We know that this is x minus h, and this is y minus k, and this is r squared. Okay? I would write that under until you get the hang of it. R squared is 25, so what is r? It's 5, okay? Now we don't have units, otherwise we would label. So our radius is 5. First thing to note there is you square root what's given, okay? Where's the center? Positive 2, positive 3. Why is it positive? Here's why I'm telling you to write it underneath. Do you see how our equation of a circle says minus? That's like the boss equation. It has minus in it. So as long as that matches up, h is just the number shown, and so is k. What if it said y plus 3? Yeah, okay. Then it would be actually negative 3. So if you want to boil that down, what we just said, h and k are the opposite sign of what is shown. This is a pattern that comes up in other, like when we do vertex form of a quadratic, it's the same. And actually uses h and k. But k is normal. And then when we do factored form of a quadratic, this will be like mid-January. Factored form is x minus p times x minus q. P and q are opposite of what we see. That's not all. Those are just some quick examples. Okay. You guys try. Quick radius, center and radius of that circle. Okay. I would start by writing that, at least till you're used to this. So r squared equals 20, and then square root both sides. This time it's not a perfect square, which is probably the most normal version. Okay, so our radius is either the square root of 20, or we could simplify that radical to 2 root 5, or we could approximate it, which I heard you clicking. So what did you get? 4.7, like that. Okay, so it's approximately 4.47. Just depending on the application that we're working in. Okay, center. This one, you don't really need to calculate. It says x plus 3, so opposite of that is minus 3 or negative 3, and then negative 4 would be positive 4. So our circle would be at negative 3 and positive 4. Okay, think about graphing this. Where is negative 3, 4 on the graph, on the coordinate grid? Where is negative 3, positive 4? Yeah, good job. Second quadrant. 1, 2, 3. 1, 2, 3, 4. Somewhere there. Okay, our radius is roughly 4.5. So it would extend. By the way, does that mean I can stick a point like right here and just eyeball it? No. Really, we can only do this in 4 directions. So up, down, left, right, safely. Okay, I'm at 4 in the y direction, and this is 4.5, so I could put a point there, roughly, maybe a little higher. Okay, in the x, y, or excuse me, in the x direction, I would need to go there, and then up, 1, 2, 3, 4, 5. So somewhere like there. And of course mine will go off the screen, but now I can start filling in my circle, right? So you get the idea? Yeah. All right. Now it's your turn. You're going to write the equation for this not looking like a circle. It's a little bit oblong looking. You know what? Let's put this as an example in our notes. This is more involved. Does that seem okay? Why did it post it up there? Okay. Go ahead and don't draw all the grid lines, just right, and then label points on there, please, so that we can get on this. She's having a stroke. Okay. That was enough time to sketch a quick circle with 2 points. First step is find the center. Actually, I would even before that write the general form of, so that is x minus h squared plus y minus k squared equals r squared. And the reason why is it gives us a structure to plug into. So we just need to find the stuff that we have to plug in. What do we need to know to have an equation for this specific circle? What do we need to know for this specific one? Yep, so HK and we need H, K, and R for this circle. That's what will make this an equation for this specific one. So for this circle. Okay, start with R. Or excuse me, start with H and K. So step 2, what's the center? Well, that's easy. Equals. What do they equal in this case? H is -1 and K is +2. Okay, so already we know 2 of the 3 things in our circle, so that's cool. And then I would go solve for R. Can we just count boxes? We can if it's either left or right or up or down. That would be fine. Here's what I mean. Just pause for a second. If it had given us, I guess on this one it doesn't work. So never mind. And it's because it's, here's what I was going to say. If it had given us maybe a circle that hits right on like that, and we could just count 1, 2, 3, then fine. Like, do that. Save yourself some work. Okay, that's not always going to be the case, though. Yeah, Zeke. Slope tells us the relative rise and run, not distance, right?
Yes.
Okay. Yep, it's that. So we're going to say if diagonal, use. It's really the Pythagorean theorem, though, right? So I don't care which one you call it. Here's the thing. For our circle equation, do we want R or R squared? We want R squared, right? So D squared, which is R squared, which is X minus X1 minus X2, which is H in this case, plus Y minus K. Was that too small? It looks like, wait, you just wrote the equation of the circle. Yeah, I did. Because that's what we're going to use. Okay? So R squared equals, what is our X coordinate? 1. 1 minus -1. So we can get this right. There we go. Plus, and then Y. Y is 5 plus 5 minus 2 squared. So R squared equals 2 squared plus 3 squared. So 13 for R squared. Everybody good on where we got that? just basically the Pythagorean theorem on those 2 points. Okay, and then step 4, we just plug all that stuff in. Plug in. Sometimes students mess that up. H, K, and R squared. Okay, so all of this comes to X, Y, comes back into our equation. So X minus -1, Y minus 2 equals 13. 13 was R squared. And then, of course, we could clean up that first one a little bit if we wanted, but this is the equation of that circle. But what do I mean by clean up the first term? Huh? Yeah, X plus 1 squared just looks a little nicer. So there's the equation of that exact circle. So find H and K, that's pretty fast, because if it's not given, then we don't know what it is. Now, there could be a case where we are given the diameter coordinates. Here, think with me for a second. Maybe I tell you the 2 end points of the diameter. How would you find the center then? Which is called the midpoint formula, right? So if I give you the end points of a diameter, you can use the midpoint formula to find the center of the circle. But then, so that's a little harder, but then the radius is easy. Well, I guess it's the same. I shouldn't say easy. Okay, just note that that's a variation of this kind of work. But you find H and K, and then you find R squared, and plug it in. That's all. Give it a shot. There are no coordinates called out on this one, so make sure that you do that first. All right, go ahead and check your work. So we had to find coordinates of the points first just by looking at the graph. H and K were -3, -1, and then X, Y for that point on the edge was -4, -4. So big thing to be careful with, make sure you get minus, negative on both when you're going to solve for R squared. Again, R squared is what we need for our circle. It's not the radius. but we don't need just the radius for our circle equation. We need the radius squared. If I said, what is the radius? Then how would you get the radius for this particular circle? How would you get the radius for this circle? Are you guys lost or just not saying? I need to know. Like, what is the radius for this particular circle? I guess we'll just sit here, like, until you figure it out. Not sure what we're missing. It says r squared is 10. So what's the radius? Say it. It's the square root of 10, right? Like, how do we get r by itself if we have r squared equals 10? Okay? So, guys, I need you to be able to, like, not just focus on process, like following a recipe, meaning I just gave you notes on hk and r squared, but we got to be able to think a little bigger to say, well, if r squared is 10, the radius is root 10. Okay? What? I have no idea. But r squared is 10, so radius is square root of 10. Good on that? Are we good on that? Good. All right, last quick thing. Graphing a circle. How? I can give you a quick note on this if you'd like it, but don't feel like you need to draw all the grid lines, please. Let's just sketch the graph. This one's kind of standalone, just graph the circle, so. And plot the center. So what's the center of this circle? 7, -3. Good job. Okay, and then step 2. Identify the radius. So what is the radius? Nope. R squared equals 4, so r equals 2, right? Maybe I should write r equals the square root of 4, which is 2. Okay, so you're going to identify the radius and graph points. Because the radius is known, we can't do diagonal, we can't count boxes. So you're just going to graph points left, right, up, and down from the center. And then you could use a compass or just do your best. Like if it says sketch, just do your best. Use a compass or sketch the circle. Okay, So let's go do those two steps. 7, -3. This is going to go off of my graph anyway, so 7, -3 is there. And then our radius is 2, so we're going to have a point at 7, -1. I guess it won't, it'll fit on here. A point at 9, -3. A point at 7, -5. And a point at 5, -3. And that kind of makes it look like it's going to be a square, but we can do our best to make it a circle, something like that. Easy enough? Whoops. How about not deleting all of it?